Hi, and welcome everybody. If you know Jonas' face, you know that I'm not Jonas, I'm Francesco. But Jonas couldn't give this talk, so it's me gonna explain to you what spectral quantum tomography is. I'm gonna start with the motivation. We know that if we have single and two-qubit gates, we can run any quantum computation, but of course, if these basic units are faulty, then in general, also the quantum computation is going to be affected negatively. Now, if it is Thanos from the Avengers who wipes out half of your qubit population, there's no really much of a hope that we can do anything about it. However, if the enemies are the more known T1, T2, crosstalk, leakage, non-Markovianity, and whatever else, then we might do something, but first we need to identify what are the errors so that then we can address them. So there is a need for a tomographic method that provides gate-specific information. And other desirable properties are that the method is fast, doesn't take too long to run it on my processor. It scales well with the number of qubits as we usually require. And as I said, we want detailed information about the gate. However, the problem is that existing methods are either one among slow, non-scalable, or providing only average error information. Specifically, main methods are quantum process tomography, randomized benchmarking, and gate set tomography. So quantum process tomography is the basic tomography you can do in a sense, but it's clearly non-scalable, exponentially. In theory, it gives you detailed information because it gives you all the process metrics, but it is not spam resistant, where spam stands for state preparation and measurement errors. So an alternative has been randomized benchmarking, which is scalable, but on the other hand, it gives you only this average gate fidelity, while at the same time, an advantage is that it is spam resistant by construction. And finally, we have gate set tomography, who gives you detailed information, and we can also say it's spam resistant, could give maybe even more information, but it's very slow. It's terribly slow. Takes hours to run at the moment, so it's not really practical for an optimization loop, for example. So these are the methods that we have. Is it the end? Well, if you've seen the Avengers Endgame movie, and if you haven't seen it, it has been a while, so it's your problem if I'm gonna spoil you something. At the beginning, the Avengers are also stuck, and what they do, they go back in time. So there are two things that I said that do not make that much sense together. And one is that we look at single and two-qubit gates. That's the building blocks that we use. But then we care about scalability with the number of qubits involved in the gate. Well, if I just want to have 1 and 2 qubit gates, I don't really care about scalability. And since this is an important thing in general in our field, and I don't want to lose my job tomorrow, I want to say that I say it in terms of benchmarking gates. Of course, scalability is a concept that is important in other areas, in terms of qubit numbers, for growing processor sizes, and so on. So the way we're going to address all of this is we drop scalability, we don't care, and that's how we get into spectral quantum tomography. Why do we call it? Well, first, how does it work? It's the following: we prepare a state, and we execute the gate U that we are interested in benchmark, and we do it k times, where k goes from 0 to a certain predefined capital K, and in the end we measure. Of course, what we actually implement in the lab is not U, but is the noisy superoperator S version of U. And what we get by this procedure is a signal that we call G of K, and the fundamental idea of spectral tomography is by playing with the K, we will have that arrows grow up or they vary as a function of K. Like the arrows induced by the gate are gonna oscillate, are going the parts in the signal that change, where the features of the signal that remains kind of constant, we're gonna associate them to state preparation and measurement errors. And that's how we separate them from the rest. That's how we get a spam-resistant method in an intuitive way. More in detail, G of K is given by preparing Pauli P mu, then executing K times the gate, and then measuring in the same basis of this Pauli, and you trace and then you sum over all possible Pauli. So it's kind of doing process tomography only on the diagonal for every K. Now, why do we call it spectral tomography? So as Tony Stark in the Avengers movie reminds us, give me the eigenvalue. Like to go back in time, he needs to ask for an eigenvalue on a model. But anyway, beyond that, why spectral? So we have the superoperator, and we can go to a Pauli transfer matrix. And then this matrix, we can diagonalize it. And in general, this is going to have eigenvalues, lambda I. And then it's going to have left and right eigenvectors. This is not a unitary. And what turns out is that if there are no spam errors at all, G of K is just equal to the sum of the eigenvalues to power K. And instead, if there are spam errors, then it all boils down to certain coefficients that we call amplitudes, K, J, which are kind of related to the weight of your eigenvalue that is also appearing to power K. So the core then of our method numerically is that we use the well-known matrix stencil technique that's been used over the last 200 years and rediscovered a bunch of times. And by using that, you can analyze this kind of series and get the eigenvalues, lambda j, some estimates for them. And then using those, we do a least square fit to find the amplitude. So it's the point about eigenvalues is that whereas eigenvectors are related to your frame, and also span is somehow related to your frame, eigenvalues are a property of a matrix that doesn't care about the frame, the basis in which you look at it. So the fact that we look at eigenvalues is making automatically our method spam resistant, together with the intuition, following the intuition that I just gave before. And in terms of giving some numbers, the required K for single qubits, the bare minimum is 4, and for 2 qubits is 28. However, to filter away some of the sampling noise, for both, we use in practice K equal to 50. And by practice, I mean that we use the IBM quantum computing on the cloud, and also the QuTech Quantum Infinity also available, that was available to us on the cloud. Before going to the results, I'm going to introduce the way that we plot our result, which is what we call spectral footprint. So here I make an example with a very simple unitary, which is already diagonal. It's a z rotation by an angle of pi/4. That is a simple trick to get then the eigenvalues of the superoperator from the unitary. And in particular, the superoperator is also diagonal, and it looks something like this. I isolate this one over there because there is always a one for matter of trace preservation. So we're going to always ignore that. And we look at these other three eigenvalues, 1 e to the I/4, a to the minus I/4, that we can plot. This is what we call the spectral footprint, where we have radially the modulus of the eigenvalues is decreasing from the central black circle, which is 1, and then it decreases, and we can see it on this axis. And then the angle is just the phase of the eigenvalue. So in this plane, for example, an over-rotation by an angle epsilon would look like having these red poles, red eigenvalues slightly shifted compared to the ideal blue one. So we do exactly an analysis for rotation by pi over 4, just about the x-axis rather than the z-axis. And we do it for the IBM Q in red. And then for the quantum infinity, we have two variants in which there are 2 qubits on the chip. We always do the rotation on 1 qubit, but in one case, we put the second qubit in 0, and in another case, we put it into the 1 state. So we can first see, and we can relate it analytically, that this distance from the center is related to your T1 and T2. And then we can zoom in into the angular deviation from ideal 45 and minus 45 degrees. And we can notice a few things. The first one is that there tends to be apparently an under rotation on IBM Q and an over rotation for the quantum infinity. But furthermore, we can also see crosstalk from the other qubit being 0 or 1 for the quantum infinity. And we can notice that this is a very small deviation, but it's statistically significant, as we verify with the f-test, sorry. And it's very small, but back on the envelope computations give us a residual ZZ coupling between the two qubits, which is just a factor of 2 away from the value measured on the experiment through an independent measurement. So it's very good. And we also benchmarked a 2-qubit gate, namely a CNOT, on the IBM QuantumExperience, where in the hardware it is realized as a cross-resonance gate. And we can observe that for the ideal CNOT, we should have just 9 eigenvalues equal to 1 and 6 equal to -1. And instead on IBM Q, we get these other ones. And the most interesting part is that there are some mathematical reasons for which for a Markovian channel, there should be at least one real eigenvalue, but we don't find any of them for IBM Q. And so this can be related to non-Markovianity. And in particular, we can relate it, like one way that this could appear is a drift in some experimental parameter, like an increase in over rotation. And we made this claim based on the fact that we do some simulation with exactly this model, and we reproduce pretty well the experiment. And specifically here, we use an over rotation with an angle of 0.05 degrees, so just very small. And we cannot say for sure because in principle, I'm putting the Pauli I tensor Y here. You could put a lot of other Paulis as we tried, and we still get similar results. But this might be related to a Y drive that is used on cross-resonance gates, and that is one of the main troubles in getting cross-resonance gates perfect. So we might have picked up that error specific to the device, although we cannot say for sure at this stage. And then I'm not going to discuss it here, but you can check it on our paper in MPJ Quantum Information, that we can identify a bunch of errors, so T1, T2 crosstalk, as we said, but also non-Markovianity in a variety of settings. And so this means that we really get this detailed information about the gate. And then we can summarize that we satisfy all the criteria, so fast, spam resistance, and detailed information. It has been tested on actual devices available on the cloud. And so the outlook is going to be the following. One piece of future work is going a bit more in depth in terms of quantitatively characterize all these errors, which we have done only up to a certain point. Then a killer application could be benchmarking logical gates, because these would comprise of a lot of qubits, but physical qubits, but it might still be a 1-qubit logical gate or 2-qubit logical gate. And in that case, we would get information about the logical error channel. And then the last thing is that what we hope is that theory and experiment are going to be aligned, and that this method is going to be used, and so that theorists and experimentalists are going to fight together against the forces of evil. And with this, I thank you very much for your attention. And this is the link. And we also have notebooks available online. Thank you very much again.